Okay, I meant to pause the video and I stopped the video, so we are starting in with a new video. Okay, yes, obviously, as soon as I stopped it, I was like, oh, of course that's why. So here's why they have to converge. The thing that I want to notice is that if n1 is less than n2, then the sum from I equals 1 up to n1 of little mi of n1 is going to be less than or equal to the sum from I equals 1 up to n2 of mi n2, but the sum from I equals 1 up to n of big Mi of n1 is going to be bigger than or equal to the sum from I equals 1 up to n of, n1 and n2, mi n2. In other words, for larger n, the minimal Riemann sums are getting larger, whereas the maximal Riemann sums are getting smaller. Why is this true? Well, the reason is because the more subintervals you have, the more chances you have to have like smaller maximums, right? If I have a subinterval that's this big and it does something like this, here is my maximum. But if I cut that in half, well then I get a new set of maximums, and the new maximums are always going to be smaller, less than or equal to the old ones. And the widths are getting smaller here. So because of this, the minimal Riemann sums form an increasing sequence. In other words, for larger values of n, the more we cut this up, the minimal Riemann sums are getting bigger, whereas the maximal Riemann sums are getting smaller. Now, it turns out that if you have a bunch of real numbers that are bounded, which we said they were bounded a few minutes ago, and they are either always increasing or always decreasing, then because they're bounded but also always going in the same direction, it turns out that they always have to converge to some number. So, also the sums are bounded, so they converge. Finally, we are done with our proof that started in the previous video. So what we have shown is that the Riemann integral of any continuous function exists. You might think that that is a really kind of a crazy thing, that we had to go through so much work just to prove that the Riemann integral exists for continuous functions, but this is like, people took that for granted for a really long time, that you could make sense of what is the area underneath a continuous function. Well, it turns out that actually proving that there is a well-defined notion of that area is a little bit complicated. Okay, so now that we have proved this, there are a few additional properties of the integral that I just want to sort of throw out there that, well, we'll talk more about these next week, but we're not going to necessarily prove all of them because, a lot of the proofs get kind of the same, but some of them are fairly easy to do. Some of them are more complicated. Let's start by looking at the following simple fact. You could interchange the role of a and b. And if you do so, the integral from b up to a of f of x dx is the negative of the integral from a up to b of f of x dx. And by the way, these two numbers, this is called the lower limit or lower bound. This is called the upper limit or upper bound. Why is this true? Well, write out the Riemann sums. The thing is that for this one, delta x is going to be equal to a minus b over n. Over here, your delta x is going to be b minus a divided by n. So you're going to get, it just flips the sign of delta x when you do this. And there we go. We've got this covered. Another thing to observe here is that the integral from a up to b of f of x plus g of x dx. This is the integral from a up to b f of x dx plus the integral from a up to b g of x dx if these exist. Now, be careful, because if these don't exist, this one could still exist. This one on the left could exist without these on the right existing. That's fine. But if these exist on the right, then the one on the left also has to exist, and it has to be equal to this. Now, why is this true? Well, just write out the Riemann sums for this one. The Riemann sums over here, I'm going to drop writing the bounds for this. These are going to look like f of xi star plus g of xi star delta x. But assuming that these limits converge, then this is just equal to the sum of the f of xi star delta x plus sum g of xi star delta x. So they're going to have to come out to be the same thing. Essentially because the Riemann sum splits into these two Riemann sums, and if the limit of these sums exists, then so does this one. We can also say that the integral from a to b of k times f of x dx is going to be equal to k times the integral from a to b of f of x dx. Okay, now I'm not going to write this one out explicitly. Once again, write down the Riemann sums. The Riemann sums for this guy are just going to be the Riemann sums for f all multiplied by k. But that means you can factor out this constant k from the sums, and that is going to, when you take the limit, those sums converge to something or they don't. The k doesn't affect it. If they do converge, then the limit on the left is just the limit on the right multiplied by that k got factored out. Okay, so there we go. These two rules together mean that the definite integral is what we call a linear functional. First of all, what is a functional? A functional is kind of like a function, except it assigns numbers to functions. Now that sounds like a weird thing, but it turns out to be very useful in mathematics. The linear part refers to the fact that you can take constants out of it and you can split it over sums. So that's what the linear part is. Of course, the definite integral, it's only really a linear functional if you specify an interval. So the definite integral on some fixed interval is going to be a linear function. Now from this, we get a couple of important facts. First of all, we can put this together to say that the integral from a up to b of f of x minus g of x dx is the integral from a up to b f of x dx minus the integral from a to b g of x dx. So that is our first important observation. Well, it's not even, it's barely an observation even, because it's really just noting, think of this as plus negative g of x, and then take the negative out of the g of x, okay? The next thing that I want to observe is, suppose that we have well, actually, we can write this more generally. Suppose that, how do I want to say this? The integral from a up to b of f of x dx is equal to the integral from a up to c of f of x dx plus the integral from c to a of f of x dx. How do you prove this? Well, one way of proving this is you split this thing into two functions. You split f of x into f1 of x, which is equal to f of x for x in a up to c, and it's 0 otherwise. and then f2 of x, which is going to be equal to f of x for x in c to b. And this works if you have a less than c less than b. And then it's 0 else. Now, we didn't show this, but it turns out that if you have a function that is integrable and you just smack part of it out to be 0, then the result can still be integrated. And then what you do is you say, well, this is actually just the integral from a to b of f1 dx plus the integral from a to b of f2 dx. Now, this works if a is less than c is less than b. What if c is bigger? Well, in that case, you do a similar kind of argument, but in that case, your second integral, the integral from c to a, ends up basically subtracting off part of the result. Because if you have a and then b and then c, then what's happening is your original integral gives you this entire region, and then you're going to be subtracting off this region here. But that should still leave you with this integral here. And the proof is a little more technical than that, but the intuition should be fairly clear. Also, if a is less than c is less than b, well, then the idea is that the area of this whole region from A up to B should be the area of this region on the left plus the area of this region on the right. So in terms of our intuition for what a definite integral is, these properties are almost obvious, okay? Now, the technical proofs, like I said, they can be a little trickier. I'm not going to go into detail with those because we already looked at the technical proof for continuous functions being integrable. I think we've seen enough technical proofs for this. Again, this is one of those things where if we were doing an advanced analysis class, I would be making you guys do all of these proofs. And they're very fun and interesting, really. But I don't think that we need to see them right now. Now, where are we going to go with this? Well, it turns out that these properties that we've proved about integrals, together with one more property, which is, again, almost obvious, and that is this property. If f of x is bigger than or equal to g of x on an interval from a to b, then the integral from a up to b of f of x dx is bigger than or equal to the integral from a up to b of g of x dx, assuming that both of these exist. And this really just follows from the Squeeze Theorem. Because what we're saying here is, essentially what happens is, for any given partitioning of A to B, in other words, you split A to B into n intervals, there is some Riemann sum for f that is bigger than some Riemann sum of g. If the Riemann sums converge, then the ones for f have to converge to something that is at least as big as the ones for g. Again, it's just a Squeeze Theorem thing. So you take this property together with the previous properties that we said about integration. It turns out that from these properties, we can prove the fundamental theorem of calculus. And that's what we're going to see next week. Now, how did people prove the fundamental theorem before Riemann came along? The answer is all of these properties that I wrote down in the last few minutes here. Every single one of them is sort of intuitively obvious if you think of the definite integral as the area above minus the area below, together with the basic properties of integrals that we've seen. There is one more that matters, by the way, the last one, and we've already kind of written this one down, but the integral from a to b of a constant is equal to that constant times b minus a. In other words, the areas of rectangles are found correctly. Well, all of these are sort of obvious, like these properties need to hold, or else our definite integral doesn't really seem like it's giving us what we intuitively expect from the area above minus the area below. So what people did is they said, look, assuming that, like, they assumed that you could make these areas be well defined. If we can define these areas, and they didn't really work, like Newton didn't worry about, can you define it? He was just like, yeah, of course you can define it. It's an area right there, you know, like proof by pointing at the area kind of thing almost. Actually, I don't know. He may have done something more technical than that. I'm not really familiar with what he specifically did, but he did not give a rigorous definition, a logically sound definition. However, all of these properties are kind of obvious just from the geometry of what's going on. Like, this fact tells me that if one function is above another, then its definite integral has to be bigger. Yeah, that's sort of obvious. And all of the other properties as well, you know, you draw a little picture and you're like, oh, yes, of course. That's kind of how it has to be. So the way people prove the fundamental theorem is just by using these properties. This is also why the fundamental theorem applies not just to Riemann's integral, but also to Lebesgue's and Daniel's, because their integrals all have these properties as well. The difference between the integrals, by the way, is simply that the Lebesgue and Daniel approaches can integrate certain functions that cannot be integrated by using Riemann's definition. So they're able to integrate some functions that you can't integrate otherwise. Now, on that note, one more thing I want to say before we get on to the fundamental theorem next week. I want to give you a couple of examples, actually, like just one example really, but we can talk about it in a couple of different forms, of a function that cannot be integrated. Consider this function. I'm going to call it q of x. It's going to be a weird definition. Q of x is going to be equal to 1 when x is rational, and it's equal to 0 when x is irrational. Weird function, I know. Here's the thing. The integral, let's say from 0 to 1 of q of x dx does not exist by Riemann definition. Riemann's definition cannot work for this, and here is why. For any n, the maximal Riemann sum is the sum from I equals 1 up to n of 1 times 1 over n, and the minimal Riemann sum is sum from I equals 1 up to n of 0 times 1 over n. So the maximal Riemann sums are always 1 and the minimal are always 0. So the maximal converge to 1 and the minimal converge to 0. That means that our Riemann sums, A, not all of them converge necessarily. In fact, they don't all converge. I want to be careful about that. I don't think, no, they might all converge. Now I'm concerned about whether they all converge. The point is they don't all converge to the same thing. That I can tell you for sure right now. Some of them converge to 1, some of them converge to 0. Therefore, this function cannot be integrated by Riemann's definition. Same kind of thing would happen if you tried to do the integral from 0 to 1 of 1 minus q of x dx. So this would be equal to 1 on the irrationals, and it would be equal to 0 on the rationals. Once again, Riemann's definition doesn't work. It turns out Lebesgue's does. Lebesgue's definition would tell you that this integral is equal to 1, and the integral from 0 to 1 of q of x dx is equal to 0. This is by Lebesgue's and Daniel's versions. However, so that's kind of one of the advantages to their integrals, is that you can make sense of this kind of thing. But like I said, they're a lot more technically complicated. So I think we're going to stop there, and we will come back to this stuff next week, and I will see you then.